Welcome to our session for cloud-based development, prototyping the automotive future. My name is Thorsten, project manager from Porsche, the other automobile manufacturer from Stuttgart. And here with me is Rafał, cloud solution architect from Grape Up.
Good afternoon.
Let us tell you a few words about the project we executed together. Where we are and where do we come from? The automobile industry has evolved further in recent decades, starting from a long era of mechanical improvements to electronics in the car, to introducing software and initial connectivity, to current cloud-based solutions. So what are the key drivers and topics these days? So we are talking about energy revolution, connectivity, mobility, and autonomous driving. But what does it mean in terms of challenges for us? We are looking at growing connectivity needs from more and more sensors and actors in the car providing services, as well as the need for more and faster data exchange with backend driven by megatrends and use cases. This is related to enriched infotainment systems providing online information, supporting the driving convenience, infrastructure, car-to-X infrastructure, so talking to traffic lights and other enabling systems, as well as swarm data intelligence usage, prediction models, further parts usage, and things like that. Use cases where this is applied is also onboard media streaming or predictive maintenance, for example, as well as park and charge services, things like that. However, there are more challenges we are facing with. The time to market for providing new connected services to the user. So this means any onboard functionality requires off-board communication, or any off-board function which needs to reach the vehicle to retrieve data and send data to it, even if the vehicle is not connected. So bridging the gap between onboard and off-board communication, regardless of the communication platform or technology used below there. As well as providing an abstraction to this kind of onboard functionality so that we are able to exchange that if we have better technology available in order to even faster exchange data, and still keeping the business and functional APIs in the car stable. And even more, we are trying to reach reusable connect functionality, so providing an onboard API of the vehicle and then building solution on top of it in the backend is another challenge we faced on. And even there, the reusability in terms of infrastructure which could be exchanged from the backend and the services across different vehicle platforms are important. These are just a few, and there are more, but these are the core ones.
These business challenges are directly linked to technical difficulties. We have to keep in mind that car is built of multiple electronic control units which host different software components. These software components are responsible for different features and aspects of the car. They control the battery, they maintain the security, as well as they provide the connection to the cloud. Such architecture makes it quite difficult in terms of delivery the software to the car. The main issue here is connectivity. We have to struggle to deliver the software to the car, but we also need to keep extra focus on building this software itself. We have to cover different edge cases, corner cases, where we, for example, cannot reach the car. We try to interact with our car, but it's not available. So we need to somehow deal with it in our software. Another factor which gives architects and developers sleepless nights is a design of such open automotive platform. It has to be open for extension, so we need to be able to adapt to new incoming features, as well as we need to be able to use existing infrastructure and integrate with existing software and existing components. Last but not least is performance. So in typical cloud native system, we have a bunch of components, I mean, like 100 or even 1,000 of different components which produce some data. And we need to handle this data. Here in this scenario, we've got this slightly different situation. We have a bunch of components deployed inside single car, but we have millions of cars. And every car produces a lot of data every second. So we have to be able to process this data in near real time. That's the main technical difficulties.
So let me tell you how we started to kick off the journey working on the prototyping of the automotive cloud. So we started small with an incubator and a few use cases to convince our stakeholders, and continue that journey actually. In that incubator phase, we focused on a few use cases. So these are the digital twin, for example, providing vehicle information, as well as license management with license enforcement and policy registries, as well as providing platform as a service, using service registries, and also the ability to invoke remote commands on the car. So we did it, or another factor in that early project phase was the evaluation of the collaboration together with our partner Grape Up to see the technical and organizational collaboration together. So we worked on a small team with 5 to 7 developers and an agile way of working, research and result oriented with very short sprints of 1 week each. And finally, after succeeding and completing that phase, so we documented the results and convinced our stakeholders on the concept so we can continue that story with a more serious ready development.
So such research and development projects are always fun for developers and architects. We have greenfield. We can play with different technologies, check if they fit our needs. But it's also challenging because in R&D projects, the requirements tend to change very frequently. And we have to be able to prove the idea within days, to deliver some POC to show the management, yes, we can do it. So we started designing the automotive cloud with very, very minimal assumptions about the architecture. We divided our components into 2 parts. We have offboard components, which are just cloud applications which are responsible for processing the data produced by cars. And we have onboard side, reflects the components we deploy in the car. That's the software which is deployed in the car. And based on this, we started building the automotive cloud. So we created a very simple application which mimics the behavior of a vehicle. So it's just behave like a vehicle. And then we created a remote command service, which is a kind of abstract component which is responsible for interaction with the car. So when we would like to interact with the car, we use this remote command service which deals with the executing that command in the vehicle. To put these things together, we set up a MQTT broker which provides us the lightweight publish-subscribe model. We can send messages back and forth from cloud to the car and other way around. And at this point, we realized this remote command service is not the best place to deal with connectivity issues and other technical stuff. So we decide maybe we can play with digital twin pattern, which is commonly used in IoT world. So we build the digital twin app. You can think of it as just a database which store the state of the car. That's the digital representation of the car in the cloud. Then we build the digital twin controller, which is responsible for synchronizing the state between the car and the cloud. To make our services accessible for our consumers, we build a platform API gateway with some security layer just to expose our services outside. As we moved along this journey, the crucial question arises where we should deploy it. We decided to start with Cloud Foundry, and we had 3 reasons to do that. The first one, like I mentioned before, in research and development projects, the requirements are changing very frequently, and we need to ship this software very quickly. Without any abstraction on top of the IaaS providers, we will not be able to do that. So using Cloud Foundry, we can focus on building the software rather than provisioning the VMs and other stuff. The second reason is the performance. Like I mentioned, the ultimate goal is to deal with the load produced by millions of cars. Using Cloud Foundry and Autoscaler, we can easily scale up our architecture and be able to handle this load. Last but not least reason why we choose the Cloud Foundry is infrastructure which exists in the VW Group. They have a battle-tested Cloud Foundry installation with extensive portfolio of different services available through Marketplace. So we were able to set up the security, different queues, different databases with just one click. That was very important for us. So at this stage of the project, we proved that Cloud Foundry works well in research and development projects, as well as homemade digital twin implementation is very helpful in synchronizing the state between the cloud and the car.
So in the next phase, continuing the journey, we are looking into providing a unified API in order to simplify the life of the service developer for onboard or offboard services, as well as swapping the communication platform. So these were the two validation points we are looking into. So a unified API means it doesn't matter where my function resides at the end. However, if it's callable onboard or offboard, it looks the same from a developer perspective. The other thing was providing the platform abstraction. While doing that, in that phase, we were working on two different communication platforms, integrating them, which were available in the VW Group. So in order to prove that we can provide a stable vehicle API and a stable business service API regardless of the communication platform. So this also enables us to focus on the time to market for connectivity functions. So we worked on that from a team perspective in a bigger team, looking into onboard and offboard teams, and in two product increments which had 3-month cycles there. The whole team was embedded in a large organization with around 20 teams from the software platform, which was looking into the vehicle platform. And this again was working according to the Scaled Agile framework, so the SAFe methodology.
So next phase of our journey involves some architectural changes as well. So to be able to support multiple communication platforms, we built an abstraction layer off top of that. So we were able to integrate with two different communication platforms. The first one is MBB, that's the in-house built by VW Group. It provides ability to transfer the messages from cloud to the car. And the second one is a wireless car, which provides more robust interaction model, and we are able to pass the messages back and forth using this solution. To provide this abstraction layer, we build a connector agent on the onboard side and connector gateway on the offboard side. Both of these components implement the digital twin pattern. They integrate with digital twin, and using these components, we were able to switch the communication platform in the runtime, so we are able to control it. On top of that, we build our services. At this point, we started building the software, the car for real. I mean, the team of embedded software developers starting building the software which can be deployed in the car. To do that, they created a Docker image, which contains some very sophisticated libraries and requires some granular control over the network. Because of that, we faced some issue because we are not able to deploy it on Cloud Foundry anymore because of this granular control which is required in this Docker image. So we decided to deploy it in Kubernetes. Because we are able to use Kubernetes, our feedback loop was very short. We can deploy this image in the cloud, which simulates the behavior of the car. We can execute the end-to-end test and validate that the changes we made are correct. On top of these services, we build the unified API. So from consumer perspective, if you interact with the car or with the cloud, the API is the same. You just change the host. Let's see how it works in practice.
Thanks, Rafał. So looking at an example for that unified API, we use the get battery example here, so a battery status of an electric vehicle. So assuming we have the same resource and resource URL from that resource onboard and offboard. The call actually is initiated by a car management service in the back end, forwarded to our connector gateway, which passes it on to the onboard side, and then invokes the actual implementation on the onboard service. So it's transparent for the developer where the function resides at the end. So let's have a look how that looks in our demo application, which we built especially for the purpose to visualize the infrastructure, because infrastructure is nice, but if you can visualize it via an app, for example, you can convince stakeholders to see the full value. So you see the two different platforms on the top executing the same functional call. So business API and vehicle API are stable. And we had also a second function sending a planned charge time in there. So this is how we actually demonstrated the value of our work here. The story continued in the next phase. The next phase, you might have heard that that the requirements to the team changed, because you might have heard that Volkswagen teamed up with Microsoft on the Automotive cloud. So we were faced with another challenge here, the IoT paradigm introduced into our journey, as well as swapping the platform again. In that phase of the journey, we were looking into still keeping the unified API, but combining it with the IoT paradigm using IoT Edge Hub and IoT Hub on that side. So these are the one components which we integrated in a new platform as a communication layer then. So the whole increment was again 3 months, but we were supported by the Microsoft team in order to integrate that on the offboard side and the onboard side in the car. Looking again on that from a developer's perspective, what is important is I will create a new service based on a vehicle API, so functions and signals available in the vehicle, and I want to build a new service on top of that in the backend. So it should be easy and simple to do so, and that is what provides the time to market and the flexibility to me. So demonstrating that, I use another example. If you imagine a location or a GPS position as an onboard resource element, we would like to provide and make this available offline for further consumption in backend services. We developed 2 components there. One is the device model collector, allowing to take the state of that property and forward it transparently to the backend, to the device shadow, as we introduced it earlier. Technically, we use the IoT Edge Hub on that for communication and the IoT Hub as a backend side counterpart for that.
What's important here, we did all these changes with minimal impact on the existing infrastructure and architecture. So our offboard services as well as device shadow was still deployed in the Cloud Foundry. We integrated it with IoT Hub, which was deployed on Azure Cloud. And internally, it used MQTT to integrate with electronic control unit. This part can be also deployed in the cloud. So we can still have this very short feedback loop and executes the test on a continuous manner. So at this stage of the project, from technical perspective, we have proven that we are able to integrate with very different communication providers, Azure IoT in this case, as well as we don't need to implement the digital twin pattern, digital shadow pattern on our own. We can use existing existing provided things, and abstract this complexity. So we can focus more on the delivering the value rather than dealing with connectivity issues and other stuff.
So last but not least, theory is nice, but having a real-world use case is better to prove that a concept or an implementation works. So we had another phase looking into a real-world use case. So we were teaming up with the business department, looking in use case, which helped us to write our user stories and shape that. And we applied our concept, the unified API, on that use case. So we'll see that in a second. For that, the team was extended, as said, by the business department, but what we also did in this phase was applying it to the real target hardware. So we got a prototype of the upcoming control unit hardware and integrated the onboard part on that. Also important were two things from the development process. So the contract first API approach, which enabled us to work in parallel with the onboard team and the offboard team, and as well as the virtual car being hosted in Kubernetes, allowing us to have short test and feedback cycles for the end-to-end, let's say, use case or chain of commands. Some more words about that real use case. If you imagine a sports car driver, there are certain speed bumps on the road. So vehicles have a functionality that they can lift the chassis to a certain lift level, depending on the surrounding and need. So that is also different between different models, but collecting such kind of data as an event and sending that back to the backend for further aggregation and processing allow you to create some suggestions based on the geographical data which was sent via the vehicle API or the digital twin to the backend, and coming up with an aggregation and a suggestion based on the geographical location to change that lift level if you're driving, because you have been provided with a suggestion from the backend what's the appropriate level to use. So this is some kind of use case which could benefit from such an infrastructure. Finally, I would sum that up that we had the big chance to use the right use cases and also make it visual using an application, extending the scope a little bit across the infrastructure to a more business-driven level, so that you can show how the infrastructure technology is applied, actually. So that was really useful.
From technical perspective, we proven again that Cloud Foundry works very well in case of R&D projects when the requirements are changing very frequently. But we also noticed that it has some limitation. When you need granular control over your runtime, you have to customize your Docker. It's better and easier to use Cloud Foundry. We also noticed that abstracting the complexity is crucial. Like we did in case of IoT Hub and stuff provided by Azure, we can abstract this complexity and focus on delivering value. All these things combined together speed up the development cycle. We also noticed that different teams need different tools. We cannot enforce them to use particular database or particular tooling, so the marketplace in this scenario is a perfect solution. Different teams can pick up different tools from the marketplace, deploy them and use them. It has also huge impact on the performance of the team.
What is also important for us is working in a collaborative manner with cross-functional teams, so the domain experts and the technical experts, having short cycles, presenting the results to the stakeholders, either in product increments or even shorter cycles according to our agile way of working. And also the flexibility, as you saw it, we needed to change and adapt to changing requirements. And that worked out really well. However, it's also important that the software runs on the target, and that's creating the most value to the business. So in our case, the prototype of the electronic control unit, so the real target hardware, as well as the backend side. So the full backend environment, how it will finally run. So in this case, again, Cloud Foundry or our Microsoft stack. But last but not least, we could say Agile works for us at our scale. So with that, I would also like to highlight our succeeding talk. So my colleagues are going to show you a more technical view on that story in a later spot. With that, we would say thanks for your attention.
Thank you.